Okay, great. So it really gives me a lot of pleasure to introduce today's speaker, Omid Ardakanian, who is an assistant professor in computer science at Alberta. Omid was my first student to work in the area of energy, so he took a big risk working with me. I think it worked out. But after working with me, he moved on to better things. He did a postdoctoral internship at Berkeley and then at UBC, and then went out to Alberta. He's been doing a lot of different things, but today he's going to talk about his work on designing control strategies for buildings, which is something that Arjun certainly cares about. So welcome, Omid. By the way, it's 6 in the morning for him, so he's really doing a lot for us. So thank you so much for that. We look forward to your talk. I'm just going to turn this around for in a moment so you can see a bit of the audience, and then yeah, you can get. I'm just going to do that here. You can get started. Okay, great. Thanks, Omid. It's all yours.
Sure. Thank you, Keshav. So it's a pleasure to be here with you today virtually. I used to attend these group meetings several years ago, so it's always a pleasure to be back and give a talk in one of these group meetings. So I'm going to talk to you about challenges in designing control strategies for the building or for smart buildings in general. The picture you see here is from the UofA campus, and you see some of the campus building. I will be referring to some of them later during my presentation. Just as a quick note, feel free to ask questions and interrupt me during the presentation. You can always put your question in the chat. Hopefully somebody will give me a nudge to monitor the chat and answer the questions, if any. Okay, let's get to it. Sorry, just 1 second. All right, so commercial buildings, and especially modern commercial buildings, house thousands of sensors. They're really larger scale distributed systems. And when we talk about sensors in commercial buildings, these are sensors that are already installed in the building, including sensors in the heating, ventilation, and air conditioning system, known as HVAC, sensors that we have in the as part of the wireless infrastructure of the building, like the access points and other things, and the sensors that we have in security and access control system, like prox card readers and QR code scanners and other things. But in recent years, there is a larger number of sensors that are increasingly being installed in buildings, including IR cameras, these sensor boxes that include multiple sensors, up to, in fact, 20 types of sensors that are in one sensor box. And we are installing some of these sensors in a new building that we will have on campus. It's being renovated and will be ready in 2 years. We have smart plugs. We have all sorts of new sensors in the building. So just making sure that everybody can see the screen, because I see in the chat that somebody says the screen can't be seen.
We can see it here. Somebody else.
I can see it too.
Okay. So maybe it's a problem on their side. Anyways, and in addition to these sensors, we also have occupants of the building, and occupants of the building can also act as sensors. They have nose, eyes, ears, and skin, so they would be able to feel the temperature in the building, provide feedback to the control loop, and they also carry some Wi-Fi enabled devices, smartphones, wearables, smartwatches, and other Wi-Fi enabled devices. So these devices also include a number of sensors, GPS, IMU, inertial measurement unit, and several other sensors. So we can also use sensor data generated by these devices in order to get a better understanding of what is going on in the building. So in addition to the sensors, we have also a large number of processors, microcontrollers, and other computing nodes that are installed in buildings. You see all sorts of devices here, Arduinos, which are like a good example of microprocessors. We have a full-fledged computer like a Raspberry Pi, NVIDIA Jetson that has GPUs in addition to CPUs and whatnot. So these sensors are in IoT devices that we have in the building, in smart thermostats, in lighting control systems, in energy management system that you may have in your garage to regulate the charge-discharge of your battery or your electric car and other electric car systems that we have. But despite all these nice things that are being installed in the building, there is still a large gap between the vision of the smart buildings and the present reality. So 2/3 of occupants, according to surveys, are not feeling comfortable in the building, despite spending more than 90% of their time indoors. So this is a big number. So most people are not satisfied with the building environment. And in addition to that, buildings account for around 1/3 of the final energy consumption worldwide. And this is partly because of the fact that heating and cooling systems are controlled based on fixed occupancy schedules, maximum occupancy assumption, and they waste a lot of energy. And at the same time, it's very hard to identify false control errors in buildings. So even if you identify faults and control errors, you always have to ask the facilities manager to help you fix these faults and control errors. So it's a process that involves human beings, and it's a very slow and time-consuming process. So really, the reality of smart buildings today is something like this. They consume too much energy, and almost everyone is like uncomfortable or not satisfied with the building environment. So now the first question that should be asked is, why is this gap so large, and how can we address this gap? In my research, I tried to identify some of the challenges that exist. The first one is, I call it measurement challenge, and this is because of the rich human building interactions that we have. So it's very hard to understand how people actually feel in the building, whether they are comfortable, how is their performance, what is their health status and well-being, and other things. And this is despite having all these sensors. These are the things that cannot be directly monitored. So you will need to have virtual sensors. You will need to fuse data from multiple sensors in order to get a better understanding of how people really feel inside the building. The second challenge is the modeling challenge. This is because these are very complex systems. The building, the surrounding environment, the climate, they have dynamics that span multiple time scales and a very large area. And as a result of this, building accurate models is always a challenging task. And lastly, I call this a generalization or portability challenge because unlike computers, buildings are not custom built. Every two buildings that you find, they look different. They have different exterior, interior, different materials are used in their construction, and so on and so forth. And in addition to all these differences between the buildings, the sensors and control points that we have in the buildings are also different. They use different protocols, they speak different languages, and they are manufactured by different vendors. And as a result, it's very hard to build an application on top of building that can be deployed to many other buildings that we may have in the same country or even in the same city. So the goal of the research I'm doing on smart building is to close the loop among data generation, computation, and control in buildings, because I believe that if we do so, we would be able to reduce cost and emissions and at the same time increase adaptability and reliability of building systems. And at the same time, we can improve human well-being, comfort, performance, and their overall satisfaction in the built environment. And the second one is perhaps more important than the first one. If you ask the companies in this space, they make a lot of money by selling products that help like monitor well-being of human beings or occupants of the building. At the same time, it's a very difficult problem. It's even more difficult than reducing energy consumption in the building. And our ongoing experience with COVID-19 has proved us that it is in fact a very hard problem to solve. So the research I'm doing in this area can be classified into three main areas or three main themes. The first one is about addressing the measurement challenge using two main ideas. One is using the sensors that are already part of the building infrastructure, also known as infrastructure mediated sensing, where you are using sensors, for example, in the HVAC system or other subsystems in order to get a better understanding of what is happening. Or fusing data from multiple sensors to create higher order sensors or virtual sensors. And this idea of having virtual sensors is even more interesting because sometimes the control commands can be treated as sensor data streams. So you would be able to look at how, for example, occupants adjust the room temperature and use this as a feedback, because if you are feeling cold, then you may increase or decrease the, let's say, set point, depending on what you're doing. The second challenge is about, the second, in fact, work that I'm doing is about addressing the modeling challenge. This can be cast as a system identification problem where you have a lot of sensor data and you're using sparsity-based techniques to recover the model of a system that is unknown. And the third one is related to addressing the generalization challenge. And I'm going to talk about this one specifically in my talk. So we have developed diversity-induced reinforcement learning algorithms and came up with some ideas to make policy evaluation more efficient in the building. So the focus of this talk, for time reason, is on the third research team. And the heavy lifting here is done by my students that you see here. So mostly TNU and Gabby and Akash, and the postdoc that worked with us for a while on this project. Okay, so here is a picture of downtown Edmonton. And as you see here, there are no two buildings that are similar. And so if you look at the outside of this building or the exterior of the building, it's very hard to find two buildings with the same architecture. And if you look at the floor plan layout of the building, materials used in the building construction, you will see even more differences. So the point that I'm trying to make here is that if you build an application, and this can be a control application, it's very hard to deploy this on the many buildings we have and expect to get low energy consumption, maximum occupant comfort, and so on. So the question is really how to learn control policies that can be used in every building. These control policies must be generalized. So before I dive into our diversity-induced reinforcement learning algorithm, I just want to give everyone a brief overview of learning-based control using reinforcement learning. So the basic idea here is that we have this environment that can be a simulation or a real building, and we have a decision-making agent. So the decision-making agent is interacting with this environment by taking some action. And this action could be changing some set points, for example, in the HVAC system, the shading system, lighting system, or other building systems that we have. And as a result of taking this action, it will see the next state or the updated state of the environment, and it will also receive some reward from the environment. In case of building control, the reward is usually a weighted sum of the building energy consumption and comfort. So this can be thermal comfort, visual comfort, or other IEQ factors, indoor environmental quality factors that we have in the building. So the goal of this agent is to learn a policy. A policy is a sequence of actions that this agent wants to take as a result of observing the state of the environment. So we can write this policy as pi of A given S. So this is really a probability, the probability of taking action as A given that you are in state S. And this policy is parameterized by theta. So because in many reinforcement learning algorithms, the policy is really a neural network. So the weights and parameters of this neural network are collected in vector theta. Okay, so depending on what kind of reinforcement learning algorithm you're using, what you do is to learn this policy or learn the parameters of this neural network. but they all do the same thing. They somehow generate samples and then use these samples to either fit some value function, which can be state value or action value. They fit this value function, and then later they try to update the policy using different techniques. And again, there are different types of reinforcement learning algorithm: value function method or Q-learning method, direct policy gradient, actor critic method, and so on. But the template is always the same, right? Generate some samples, try to fit a value function, or evaluate the reward, and then update the policy somehow. Okay, so that was my 1 minute introduction to reinforcement learning. Now, we used a very sample efficient reinforcement learning algorithm. In fact, 3 sample efficient reinforcement learning algorithms in our prior work. And we tried to control a simple building, a building that has only 5 zones, 4 perimeter zones and 1 interior zone. Okay, so it's a very simple building. It's simulated in Energy Plus and COBS, the simulation environment that we built in the lab. And we wanted to see how we can train different decision-making agents. As you see on the right-hand side, this is showing the learning curve of our reinforcement learning algorithms. Y-axis is the reward, x-axis is the episode, and each episode is 1 month of interaction between the decision-making agent and the building environment. So if you want to learn a useful policy, and here by a useful policy, I mean a policy that is better than the rule-based policy, you need more than 200 months worth of data. It's very expensive to collect this much data from a building. As a result, we are facing, in fact, an important challenge in training reinforcement learning agents for building control. So there are 2 ideas that can be used.
A quick question. Sorry.
Sure.
I may interrupt. Can you hear me? Yeah.
No, please go ahead.
So my question is, what was the reward in the previous plot?
Good question. So it's a weighted sum of energy consumption and thermal comfort and visual comfort, because in this case, we were controlling 3 different systems.
Okay. Mm-hmm. What was the third one? Sorry.
Visual comfort. Mm-hmm.
Thank you.
Sure. So there are 2 different ways that we can address this problem. The first one is that if the RL agent is trained in the real building, right? So we can train always the RL agent in the real building rather than interacting with the simulation environment. But this means that occupant comfort and energy consumption are likely be very poor in the earliest stage of training. And this is because we are trying to explore a very large state action space, right? When the agent is exploring this large state action space, it's still learning, and maybe in the early stage of training, you do not have a good policy. So you have to let this run for some time, and this could be months until you learn something useful. So this can obviously happen in a real building because we have real occupants, and everyone will complain to the facilities manager that we are not comfortable. So the second approach is to train the reinforcement learning by interacting with the simulation building, but this approach has its own limitations because the simulation and real buildings, they can be quite different. And it's very hard to make sure that we have grounded simulation. So the third approach that I'm going to talk about today is trying to reduce the training cost of reinforcement learning by training some policies on a prototype building. And this prototype building can be a controlled environment or can just be just a model simulation we have in our simulation, and then find a way to transfer these policies to the target environment. And then we can retrain the agent on the target environment to maybe gain more experience and adapt to the environment of that building, of the target building. So this idea is interesting in theory, but in practice, there are also a lot of different challenges that must be addressed. So just to tell you a little bit about this, we want to train reinforcement learning agents on what I call the source building. The source building is really this prototype building or the controlled environment that we have. and deploy this to the target building. And this target building can be a novel environment. It can be a building that is completely different from the source building that we had. So what we can do is to, again, use the same reinforcement learning algorithm we had. Once we are confident that this is a good policy, it's a reasonably good policy, we can transfer this to the new building. But in practice, this idea doesn't work because we have different state and action spaces in the two buildings, right? So we may have a different number of control points in our target building or a different number of sensors. And as a result, the policy that you learn in the source building cannot be readily transferred to the target building. So that is proposal one. Proposal two is to use the multi-agent reinforcement learning framework, in which we have a particular agent for every zone of our building. And this is going to be helpful because every zone, as you see on the right-hand side, has its own control system, local control system. It's called variable air volume system, for example. And inside the variable air volume system, you have multiple sense and control points. So maybe there is more similarity between VAV systems rather than buildings in general. So one can argue that in most VAV systems, we have the same set of sensors and the same set of control points. So maybe if we learn this policy for one zone and transfer this to the most similar zone in the target building, we can partly address this challenge we are facing. But the problem is that the optimal policy that is learned in the source building may perform very poorly in the target building because, again, there are some differences between these zones. So doing this is not going to help, although it will help in the sense that maybe we get the same MDP in the source and target building. MDP stands for Markov Decision Process. So lastly, another thing that we can do is to train a diverse population of reinforcement learning agents. And I have to define diversity, just bear with me for a second, and then assign the most suitable policy among these agents that we have to each zone in the target building. So the first thing is that, what is this policy library? It's a collection of policies that are learned in the source building using different parameters, theta, theta prime, theta double prime, and so on and so forth. So if we learn all these policies by interacting with the source building, then assuming that we have a small amount of log data from the target building, we should be able to very quickly evaluate these policies and say whether they're good or not. So let's say that we use this log data, we use policy evaluation techniques that I will talk about, and we identify the best policy for our for the zone that we have in the target building. And we transfer this policy to the target building, we retrain that policy on the target building. But this has to be repeated for every zone in the target building. So I find the best policy for this zone, and then I move on to the next zone. I will repeat this process. I will find a new policy. So if you want to take this approach, there are three main questions that should be answered. First, what is diversity, and why is this useful for transfer learning? So we are going to talk about this a little bit. I will show you the mathematical formulation of this diversity loss that we are going to introduce. And lastly, we will see how we can efficiently identify the high quality policy or the best policy that we have in our policy library. So the intuition behind this idea is very simple. Imagine that we have a skill learned for a specific task, right? If you just know one skill, it's not going to be perhaps useful in another task. But somebody who knows or learns a diverse set of skills, right? If you have a diverse set of skills, then you are more likely to be successful in any new task that is presented to you. So now imagine these skills are the policies that we have in the policy library, and the task is the optimal control task or the reinforcement learning task. So there are two main types of diversity that we can talk about. The first type is called policy diversity. So The idea is to learn policies that are to some extent optimal, but at the same time, they are different from one another. And if we want to do that, we have to augment the loss function of our reinforcement learning algorithm. So in addition to finding a policy that optimizes the loss or maximizes our reward, we also have a second term that ensures this policy or forces this policy to be as different as possible from the other policies that we have learned so far. And this is called policy diversity. So if you want to see how the loss function is written, it's essentially the weighted sum of the regular reinforcement learning loss you have for your algorithm and the diversity loss that we are going to introduce. And the second type of diversity is environment diversity. If we learn policies on multiple environments rather than a single environment, then maybe it's better for generalization. So the policies learned through interaction with these environments will be added to our policy library. So whenever we are talking about this policy library or the collection of policies we have, it's the policies that are learned on multiple environments using this diversity-induced reinforcement learning algorithm. So how can we define a measure of diversity? There are different approaches to this. There are, in fact, recent NeurIPS ICML papers that talk about this problem. But our approach is what I'm going to describe here. A policy pi is said to be different from another policy pi prime if for every state action tuple that is visited in the trajectory taken under this policy pi, these two probabilities, the conditional probability of taking action A given S under policy pi, and the conditional probability of taking action A given S under policy pi prime, they're sufficiently different from one another, but these two policies agree on the value of state S. So both of them have the same estimate. They have actually very small estimation bias compared to each other. Both of them have the same state value for this particular state, but they act differently on this state. So that is very briefly how we define this notion of diversity. And in order to measure that, you can use this ratio of pi of A given S to pi prime of A given S, or pi prime of A given S to pi of A given S, whichever is greater. So this allows us to measure the difference between these two policies for a given tuple. Now we have a trajectory, so we have to take the sum over all state action tuples that are in this trajectory. So obviously there are some numerical errors here, and at the same time this ratio can be unbounded. So we have to clip this at a certain level to make sure that this is this makes sense, right? So again, as I mentioned, since we have multiple state action pairs, we are going to take the sum over all of these clipped ratios to define a measure of diversity. And if we want to make sure that this policy is different from multiple policies that are learned before, again, we are going to take the sum over all policies that are learned before, because we want to maximize the distance, not just from one policy, but from a collection of policies that we have learned so far.
I have a question. Sorry if I may just ask. What do you mean by the policies agree on state S? On the vector, they agree.
That's a good question. It's in fact the denominator of the numerator of this thing that you see here. It's what we call the estimation bias, meaning that the expected return starting from a state S under policy under this policy, right, is going to be very close to the value function of policy pi prime for a state S, right? So we are using the value function here to define whether they agree about the state of the value of the state or not.
Okay, but that assumes that both policies also have a similar outcomes. It kind of converge to an overall similar value function.
They don't have to have a similar outcome in the sense that they don't have to reach the same state at the end, right? But they have they will gain some reward, right? We are just comparing the expected reward under different policies here, or what they think the value of this policy is going to be starting from state S.
Okay, yeah, thanks.
Sure. So this is essentially what I explained in the previous slide, right? And PyLearn is this policy library that I was talking about. It's the set of policies that have that we have learned so far. So we are taking the sum over all of these policies. Okay. So we tried to.
Sorry, Omid, what is capital G?
So capital G is our goal. It's essentially the total reward of this trajectory, right? Under policy pi, so that we had a trajectory. So this is the total reward of this trajectory starting from a state S.
Wait, so, but GX is not, it's not, it doesn't have pi in it, right? Or does it have pi in it? It's just implicit.
So it's generated by this policies, as a result, it has pi in it, right? Because this is the trajectory taken under this policy.
Okay, so pi is implicitly inside GX.
Mm-hmm. Mm-hmm.
Okay, great, thank you.
So we use this idea, and we just wanted to see whether this works or not, right? Now, what I'm showing here is the performance of policies in our policy library, and we had 800 policies in our policy library. We trained these policies. We learned, in fact, these policies on a source building, and we transferred them to a target building that is different from the source building. The y-axis here, or the rows that you see, there are different zones in the target building. And the x-axis is one of the terms we had in the reward function, which is our total monthly energy consumption. Okay, so now these boxes and the whiskers that you see, they are showing the range of the reward that or the range of, in fact, energy consumption under different policies. And you see a very wide range for some of these zones. Now, what are the asterisks? The asterisks are, in fact, the policies learned without the diversity loss, meaning that W, which is our diversity weight, is set to 0. So if you set W to 0, you get these policies, right? And as you see, compared to the other policies, to the other 800 policies that we trained using the diversity loss, some of them are performing much better than the optimal policy. Because if you set W to 0, you're going to learn the optimal policy for the source building. But when you transfer the optimal policy to the target building, it doesn't have to be optimal. And in fact, as you see here, most of these asterisks are on the right-hand side of the vertical line. Vertical line is the performance of our default controller. So they are even worse than the default controller. But there are some good policies in our policy library that are on the left-hand side of this vertical line. The question is how to identify them. But this shows that if we have a good method to identify these policies, this is a very interesting idea. We would be able to get better performance even without retraining on the target building at initialization.
I have a quick question on that.
Sure.
How do the policies, the diverse policies, perform on the source building? Are they all close to optimal, or are they very divergent in terms of absolute performance?
Sorry, I didn't catch the first part of your question. Can you repeat that?
How do the policies, the diverse, like the policy library, how does it perform on the source building? Are they all close to optimal, or are they like very divergent?
Yeah, so they are very close to optimal in the source building. Yeah, so they're very close to optimal. They are, in fact, learned without this diversity weight. So they should be near optimal. They're never optimal because we stop early, right? At some point, at some episode, right? But they are very close to optimal, and that's why I call them near optimal policies in the source building.
On the absolute scale, these are just improving performance like 1.5% or so, right?
They're improving performance for that I think building, right, by a small amount. But in this experimentation, we assume that all other zones in the building are controlled using rule-based controllers, using the default policy. So this is just for one of them, right? We got some improvement in one of the zones.
Okay, got it. So this is just leave one, take one out and replace just one zone with. Okay, thank you.
Yes. Okay, so now there are different approaches that we can take to find the best policy, to evaluate policies, and to select the best one. The naive strategy is just brute force search, right? So you run every policy you have in your policy library on every zone in the target building. And if you have enough time to do that, then you would be able to measure the energy use and comfort under all these policies for every zone. And then you select the best one. This is going to be too expensive. So we want to do better than this. And we use existing off-policy policy evaluation techniques. So the idea here is that we can evaluate the performance of policies learned in a training environment without online interaction with the target environment, right? So if we cannot interact with the target environment, then how can we learn, how can we estimate the performance of this policy? And the idea here is that we have some offline data set, and this is the data that we collected under, say, the default controller in the target building. So we have some log data under the default controller from the log building. We use this data to evaluate our policies. So there are several different techniques for offline policy evaluation or off-policy policy evaluation. Inverse probability weighting and variance of inverse probability weighting are some of the most popular techniques, and they're using importance and rejection sampling, right, to reweight the rewards that are obtained in the source environment according to the trajectories that are seen in the target environment. So this is essentially using both importance sampling and rejection sampling. But since we are using rejection sampling, it means that this is limited to the discrete action space. For continuous action space, the probability of taking an action is always 0 because this is a continuous space. So rejection sampling doesn't really work in the continuous space. If you want to have a variant of these methods in the continuous space, you can use kernel density estimation techniques in order to be able to essentially evaluate a policy in the continuous space. And this is the idea of Gaussian kernel. Gaussian kernel uses a Gaussian kernel in the kernel the density estimation technique to, instead of rejection sampling, to be able to estimate the performance of the policy. And there are some other techniques that we borrowed from neural architecture search. So these are some heuristics that are often used for pruning neural network architectures or for selecting the best architecture among a set of candidates that we have. So they use different heuristics, as I mentioned, but the idea is that they usually compute the loss or the gradient of the loss and use this gradient somehow in their heuristic to tell at initialization or before training, right, whether this neural network is good or bad. And there are, again, a wide range of heuristics that can be used depending on which zero-cost proxy method you use. But since the policy itself is a neural network, it means that you would be able to apply the same techniques to the policy, right? Instead of selecting the best neural network, here I'm selecting the best policy using, again, techniques that are very popular in neural architecture search in AutoML and other domains. So this is another approach that we can take. So now, very briefly, before I show you the results, what we have done is that we use these techniques to build this policy library and very efficiently identify the best candidate policy for every zone in our target building, which can be a novel environment. And we showed that the selected policies, if we combine them and use them together, they're going to save us up to 30% on energy consumption in the new building, right, during a winter month. And this is without sacrificing thermal comfort. Okay, so as I mentioned, this has to be done using the multi-agent reinforcement learning framework. Otherwise, we won't be able to transfer policies to the new building because we do not have the same MVPs. So in our multi-agent reinforcement learning framework, every agent is responsible for changing the damper position in its respective zone. And we have multiple zones, so we have multiple agents. The state or the observations that are given to every agent, it's coming from virtual or physical sensors that we have in the building. Zone temperature, humidity, occupancy level, outdoor temperature, solar radiation, and hour of the day. And then each agent decides on the minimum damper position of that VAV system, of that variable air volume system we have in that zone. And the reward is the energy use of the respective VAV system. So note that these agents are not, in fact, communicating with each other. So they just see their own reward, and they're trying to maximize their own reward. So now the big picture is this. We had our source building. It was a prototype building from Department of Energy in the States. We modified this building by using different occupancy schedules and using different blind settings. So we added blinds to the building, we opened the blinds, and then we closed all the blinds to get a diverse set of environments. So that is for the environment diversity part. So we have now multiple environments. We trained our reinforcement learning agents by interacting with all these environments. And this gave us 800 policies in our policy library. The next step is to represent these policies in an m-dimensional space, right? How can we do that? There are many different ways to do that, but what we did is to sample some states from these policies, from the states that were in fact visited under these policies, and then we found the corresponding action that should be taken under this policy. Then we use all these actions to represent the policy in an m-dimensional space. So then we clustered these policies in that space. And this is the interesting part, because as I will show you later, there is a certain structure in this space, and some of these policies that are performing better, they're closer to each other. So we clustered all these policies. We sampled some representative policies from every cluster to evaluate the performance of policies that we have in that particular cluster. And then we ranked these policies and found the best cluster using the log data that we had from the target building. Once we had the best cluster or the top cluster, then we sampled policies from that cluster and we evaluated these policies, again using the log data that we had from the target building. And eventually we found the best policy for every zone in the target building. We transferred that to the zone and we could do retraining on that zone. So this is just showing different, again, zero cost proxy and off policy evaluation techniques that can be used for evaluating policies. The rows that you see here, or the y-axis, is different techniques that I talked to you about. And the x-axis is showing either the Spearman correlation, which is the Pearson correlation that compares two different rank sets, or regret at 5, which compares the value of the top 5 policies under this policy evaluation technique. So it compares the value of these top 5 policies with the actual top 5 policies that we have if we had ground truth data. So this is showing that the Spearman correlation is better for Gaussian kernel, which means that Gaussian kernel is usually more successful in getting this rank set more accurately compared to the other methods. And then the regret at 5 is better for some of the other techniques that we have. So some of the other techniques you see here, they are again more successful, including the zero cost proxy method called SNP. So this method is more successful in finding the topmost, in fact, the five top policies that we have. So as a result, Gaussian kernel is used to identify the best cluster, and then SNP is used to identify the best policy within the top cluster. Okay, so now I will talk a little bit about the experiments that we ran. So we had 3 buildings, a 1-story 5-zone small office building located in Denver, Colorado. We had building B, a larger building. This is one of the prototype buildings from the Department of States. and this is located in fact, we changed the location. It can be in Denver or it can be in San Francisco because we use different weather data. And the building C is a building that we had in the Middle East, but since we didn't have log data from that building, it's actually a real campus building. But since we didn't have the log data from that building, we didn't have, sorry, the weather data from that environment, from that country. So we had to transfer this building to San Francisco. And we assume that this building is now located in San Francisco. We use San Francisco weather data to evaluate the goodness of the policies that we have for this particular building. So this is just showing the CDF of different clusters that I showed you earlier, right? The x-axis is the monthly energy consumption in the megawatt hours, and the y-axis is the CDF. So some of these clusters, as you see here, if you look at the policies in that cluster, in these clusters, they are much better than the policies that you find in the other clusters. For example, the green curve that you see here, this is for the top cluster. So if you sample one policy from every cluster, there is a very small probability that you get this wrong. But it is still possible, right? You may be very unlucky and you sample a point that has high energy consumption. You sample a policy that has high energy consumption, and you sample the policy that has the lowest energy consumption from another cluster, right? That is still possible. But if you sample multiple policies from that cluster and take the average performance, it's very hard to make a mistake. And that's exactly what we did. We sampled multiple policies from every cluster, and we compared the average performance of these policies to find the best cluster.
Omid, there's a clarification here. Why didn't you do all of them? I mean, is it too expensive to do?
Yeah, we just wanted to do this very quickly.
Okay. I mean, the thing is, your building is going to be there for the next, 30, 40 years. You have plenty of time.
Yeah, so that's a good point. It depends on how often you want to do this, right? If you want to update your policies, right, every now and then, then you may want to speed up the whole process. But if you want to just do this once and forget about it, then you're right. We can just try all of them.
Okay.
So now I will show you the performance of these policies compared to the baseline. The baseline here is the default control policy. It was a rule-based controller we had in that building. Here, all the policies in the policy library are trained by interacting with building A, and they were transferred to control the environment of building B Denver. So B Denver is building B located in Denver, Colorado. It's the same city as building A because building A was also located in Colorado. So here we are just changing the environment of the building, but the weather data is going to stay the same. So we are comparing with two policies that are learned from scratch, in fact, without knowledge transfer. So a single agent reinforcement learning algorithm learned using PPO, proximal policy optimization, and a multi-agent reinforcement learning algorithm. It's learned again using PPO. What you see here is that their performance gets a little bit better as you increase the number of episodes that you have, because they are learning by interacting with the building system. Although in MARL, at some point it starts to in fact go up again. The problem is that these agents are competing with each other in the multi-agent setting, and it's not guaranteed that they will learn a policy that is eventually reducing the energy consumption of the whole building. But now let's compare them with the green line. The green curve is showing the performance of, or the learning curve of our proposed method using GK and SNP. These are the two policy evaluation techniques that we used in the first stage to find the top cluster, and then in the second stage to find essentially the best policy within the top cluster. So if you compare the performance of these two with our method, the gap is huge. If you compare the performance of our method with the optimal case, and the optimal case is not really the optimal energy consumption. it's the optimal assignment of policies in our policy library. Meaning that if we had gone through data and we knew which policy in our policy library is better for which zone, this is how much energy will be consumed in the target building. And here is
one quick clarification question. So the MAR and single agent RL, they are both just training. Like what exactly are they in this plot? They're training on just on the test on the source.
Yes, on the target building. They're just training on the target building.
Ah, okay. So it's okay. Gotcha.
Yeah. And for our method, we retrain that policy. So if you look at episode 0, this is the performance of our controller at initialization. The point here is that the performance at initialization is much better than single agent reinforcement learning and multi-agent reinforcement learning, and also compared to the default controller. And after retraining, it gets even better, right? But at initialization is what we are mostly concerned about. So optimal is just optimal assignment, as I mentioned. It's not really the optimal energy consumption. And if you look at the gap between the default controller and the performance of our controller at initialization after retraining, you see that we can save a lot of energy by using transfer learning. We did the same experiment. Sorry,
one clarification. So if you had MPC, where would that be? I mean, would it be below the optimal?
That's a very good question, Keshav. It will be below the optimal, right? If we had, no, it will not be below the, it will be below the rule-based controller.
Okay.
It will be very close to the optimal if we had a good model.
Yeah.
The problem with MVC is that model identification in itself is a very difficult problem, right? But if you have a good model, it will be below the default controller performance, but it will be very close to the optimal one.
But what if you had LB-MPC?
So LB-MPC will have the same, more or less the same performance. It's a little bit better than MPC, but the performance I was talking about is in fact for LB-MPC, where we use data to learn the model, right? Yeah. So we are, and its performance is also going to be very close to the model-based reinforcement learning, because in model-based reinforcement learning, you also have a model for planning. So yeah, but I don't have these graphs here. We did in fact these experiments to compare with model-based methods as well. Great, so yeah, so now this time we transferred to B San Francisco. So this is the same building, building B, but this time we changed the weather data. Now we are transferring to a different building in a different climate. Okay, and you see the same trend, right? SARL and MARL, they are learning very fast. And this is interesting because it looks like in the previous case, they didn't really know how to adapt to the new environment. But now that we changed the weather data, they by interacting with the building environment and the surrounding environment, now they are able to learn better policies. But there is still a huge gap between the default controller performance and our controller performance. And the same thing can be done in building C. Building C was a real building. So this is the model of a real building we had. We assume that building C is located, I think, in San Francisco. So in this case, again, you see the same trend. Can save a lot of energy by using our controller compared to the default one. But there is still a gap between optimal assignment of policies and our method. And this is what we are working on today to close this gap, to improve this method and even get closer to the performance of the optimal control, optimal assignment in this case. So that's for building C.
One final, sorry, just one final clarification. So by optimal, basically the problem is you're not finding quite the right policy within your policy library. That's
right. Yeah. So we fail in identifying the best policy, not for every zone, but for a subset of zones, because we have to repeat this process for every zone in the target building, right?
Yeah, makes sense.
So it's quite possible that for some zones in the target building, we cannot identify the best policy. And that is the gap that can be addressed using better heuristics, using other methods for offline policy evaluation. Off policy evaluation. Okay, so just to wrap up, what we discussed today is that having access to a set of diverse policies might be better than just learning the optimal policy and transferring that policy to a novel environment. The second takeaway is that high quality policies in our policy library can be efficiently identified thanks to important sampling, rejection sampling techniques, and all these off-policy policy evaluation and zero-cost proxies that we have used. So we borrowed these ideas from reinforcement learning and from the supervised learning domain, especially for neural architecture search. And lastly, we can save up to 30% on energy consumption in the earliest stage of training, even without retraining in the 3 buildings that we had. And then the reinforcement learning-based controller outperforms the default rule-based controller without retraining and without sacrificing thermal comfort. So in terms of thermal comfort, we did some comparison. I didn't have the graphs here, but we looked at thermal comfort as well. And we are doing very, very similar to essentially the rule-based controller. So the average PMV that we calculated under the 2 policies are very close to each other. PMV stands for personal mean vote. So Keshav is very familiar with that.
Predicted mean vote.
Predicted mean vote, yeah. Okay, yeah, so that's it. With that, I will conclude my talk and we'll be happy to take any more questions.
Thanks, Omid. Okay, so we have time for very few questions, mainly because number one, we're asking a lot of questions, and number two, there's some people going to take over this room in like about 2 minutes or so. So any other questions from anyone? Or if you're online, please just unmute yourself and ask a question. That's all. Anybody in the room? Yeah,
go first. Okay, then one quick question was when it comes to, yes, like 2 forms of diversity. One is kind of policy-based diversity and the other one is environment diversity. Have you done some kind of evaluation study where you looked into which form of diversity is more important, or like which produces the better policy library if you had to leave one out?
Mm-hmm. So that's a very good question. In fact, what we found is that policy diversity is much more important than environment diversity. I have another graph that I didn't show, where we looked at policy diversity only, environment diversity only, and then the combination of policy diversity and environment diversity. And we found that policy diversity alone gives us a lot of improvement. So if you combine this with environment diversity, you get a little bit more improvement, but most of the improvement we got, in fact, comes from using policy diversity and not from environment diversity.
Okay, we should, Felipe should ask the last question, and then you can follow up offline. Yeah. Felipe?
Yes, thank you for the talk. I would like to know like 2 simple questions. So the first one, I see that it's very important, like what you are building for when you're deploying this to the building, like for the first time, because you have to increase the prediction very fast. But I would like to know if your system, it has like the possibility of like learning from the data you're collecting after you install your system, like in some iterative form. And the other question is, if there's like a tipping point that is better to use the data you collected for creating your like training your own model for that specific building and like left the reinforced learning behind. I don't know if I was clear with my question.
Mm-hmm. So the second one is a hard question to answer because there is a lot of work on combining classical control and in fact modern control using reinforcement learning together with say model-based controllers from MPC to other techniques, right? And there's some also hybrid strategies where you do not completely switch from one strategy to the other one, but you try to use both learning-based and model-based techniques together, right? So it's a tough question. I do not have any answer right now, but this is something that can definitely be explored, right? Is there any point after which it makes sense to completely switch to model-based techniques, or perhaps to use them together? using a hybrid strategy? So it's a hard question. For this first question, if I understood this correctly, you're saying that we can always learn on the go, right? And this is exactly what we do. We learn on the go, because as we collect more data, you can always retrain your reinforcement learning agents on that building. So I'm not quite sure if I understood your question, but if you're asking whether this can be always updated, we can definitely do that. As we are collecting more observations, we gain more experience, we can always update the policy.
Yeah, perfect. It was a question. Thank you.
Great. Thanks again, Omid.
Thank you.
Thank you. I'm going to stop the recording now.